Recording is live, the mic is working. Welcome to another week of Chem 1A. This week we are finishing our discussion on reactions and moving on, of course, to our next topic in the curriculum. But a couple of things on your plate slash some new changes. Number one, today is our final day of reactions. Do know that we have an experiment right after, so we do have a wet lab today at 1:30. If you need to change before the lab, be sure to do that because, of course, if you're not dressed appropriately, I cannot allow you to do the lab. The other most important update that only just occurred over this week is based on the head of the department's what she observed. She has canceled the lab exams. So we will not be doing a lab midterm exam. We will not be doing a lab final exam. She has decided that amidst all the other expectations we have of you for lab, it just might be too much slash overkill for what she wants to accomplish this semester. So the syllabus on Canvas reflects that change. Our first lab exam would have been that day of workshop 8. That's Monday, the 27th in October. That's no longer the case. And our lab final would have been Wednesday, November 26th. That's us replaced with a regular workshop. So all of this is to say that the only tests or assessments that we have are in lecture only. You will not have a lab midterm, nor will you have a lab final. You are still expected to carry out, taking notes, taking observations down and all that stuff, because as you go further into the labs, the procedures don't hold your hand through everything. For example, today we're carrying out reactions. We'll be observing chemical reactions. The procedure is a little bit light on wording because, of course, you're expected to figure out a lot of other things on the way. Do we have any questions on the schedule or the syllabus? No? Okay. All right, let's pick up where we left off. The last thing that we talked about was redox reactions. Just as a recap about it, redox stands for reduction and oxidation, and it involves the direct transfer of electrons from one reactant to another. One reactant will lose electrons. That's given the term oxidized. Other reactant will gain electrons. That's given the term reduced. The key thing about reduction and oxidation is that they must occur together. If there is one reduction taking place, there has to be one oxidation. If there's two reductions, two oxidations, three, and so forth. In Chem 1A, you will only ever see one reduction and one oxidation taking place together. But the key point is they must occur together. Oxidation is defined as the loss of electrons. Reduction is defined as a gain of electrons. The mnemonic that's most commonly used to remember this is called oil rig. Of course, the big thing is that you need to remember that when we talk about gain and loss, we're specifically talking about electrons. The one adage that we stated was, since elements in a compound are already ions, elements that are by themselves in their reference/normal state have a charge of 0. We went through a few examples during class in which I showed you in this case right here, we can observe that the aluminum by itself, an element by itself in its reference state, in its normally occurring solid state, will have a charge of 0. On the product side, it exists as part of a compound, which means it does have an ionic charge, aka +3 because it's in group 13. That's how we're able to note that the aluminum changes from 0 to 3. Similarly, if we apply the same logic to copper, we will see that copper ends up 0, aka by itself, but in the reactant, it had a charge of +2. Nothing, of course, happens to the chlorine. It starts off -1, it ends up -1. So by all intents and purposes, we can ignore its presence. By writing a generic equation to represent the change, Al0 to Al3 plus, copper 2 plus to copper 0, we can very quickly identify whether or not something has been oxidized or reduced. I gave you the mnemonic, oil rig, loss of electrons and gain, but you can also use visual mnemonics such as this chart over here. Using a generic scale where the right is positive and the left is the left is negative. To the right is defined as oxidation, and to the left is defined as reduction. In the case of aluminum 0 to aluminum 3 plus, we headed to the right. This was an example of oxidation from 0 to 3 plus. In the case of copper 2 plus to 0, we go from +2 to the opposite direction. This is reduction. The best part about redox is that once you've identified one, you can very quickly identify the other. In other words, even though we systematically identified that copper was being reduced, what you also could have done is recognize, well, if aluminum is being oxidized, that means the other one must be reduced, no question about it. Now, as of right now, these reactions, these half reactions, only show change in charge. They do not show how many electrons are transferred. We can incorporate the electrons into the equations using two basic ideas. In the case of illumination, electrons are products, hence why they appear on the product side. In the case of reduction, electrons are reactants. That's what tells us that in the case of oxidation, electrons will be on the right, and in the case of reduction, electrons will be on the left. The subsequent question, of course, is how do we know how many electrons should we have? To answer that question, we simply look at the charge. In the case of aluminum, we saw that we went from 0 to +3. That means that we lost 3 electrons specifically. Copper started off 2 plus and ended up neutral. That's what tells us we specifically need 2 electrons. Now, as of right now, these half reactions are overall unbalanced. What do I mean by overall unbalanced? Well, simply put, the electrons that aluminum gives up, that it loses, has to go somewhere. We can see that 2 of them go to the copper. In other words, there's just a loose electron just sort of floating around, not knowing what to do. This does not work. We need to have an equal number of electrons. So to balance the half reactions, we're going to multiply each half reaction so that we have an equal number of electrons. To get an equal number of electrons right here, we identify the LCM, aka the lowest common multiple. This may be a term you remember from high school algebra. The lowest common multiple is quite simply the product that those two numbers have in common. The best way to get it is to simply multiply the numbers by each other. In other words, 3 times 2 is 6. 2 times 3 is also 6. We want these electrons to be equal, so that's what tells us what we'll be multiplying by. The entire top half reaction gets multiplied by 2, such that we have 2 aluminums and in total 6 electrons. The bottom reaction gets multiplied by 3, such that we end up with 3 coppers overall and a resounding 6 electrons. As a result, we have now fully balanced half reactions, presumably the final answer to any such questions. I want you to recognize all of the key features that make this so good. The reactions show the number of electrons. It also shows where the electrons are. It shows the specific change in charge or charges. It's also balanced. These are the 3 key things that I look for a fully correct half reaction. I want to be able to see the number of electrons. I want to be able to clearly see on what side of the reaction they are. I want to be able to see the change in charge. And of course, ensure that the whole thing is balanced overall. Before we move on to our latest topic, does anyone have any questions about redox? Okay. Our next topic within redox is titled Agents of Redox. If you recall, this was a part of the question on your workshop last week that at the time we weren't able to do. But today we're going to go over the concept. There are 2 types of redox agents. There are reducing agents. There are oxidizing agents. Now, the principle behind these two terms is remarkably simple, even though it may not be intuitive. A reducing agent is a compound that has been oxidized. An oxidizing agent, on the other hand, is a compound that has been reduced. So these are the very simple, straightforward definitions, but recognize the fact that some of these terms are flipped. A reducing agent is one that has been oxidized. An oxidizing agent is one that has been reduced. So let's take a second using one of the reactions we just did, the aluminum with the copper, to identify what the reducing and oxidizing agents are. Yes, here we are. All right. So this was the reaction that we already uncovered, the one that we just spent a few minutes on. We already know, of course, that aluminum gets oxidized and copper gets reduced. We spend time about this. We spend time thinking about it. We spend time analyzing it, and we're confident of our respective answers. The top reaction being oxidized and the bottom reaction being reduced. To identify the agents, it's simply the opposite. This half reaction represents a case where the aluminum was oxidized. Any compound that has been oxidized is known as the reducing agent. Similarly speaking, the copper that has been reduced is the oxidizing agent. Oops. Just to show you what I've written, because I see that there's a thing blocking it. Oxidizing agent. Now, I don't expect you to have this document at the ready, but I did want to do one of the questions from the reactions workshop. That way we can do one full question now that we have this topic in hand. So workshop 3 reactions. A couple of the ones that we did the first page, page 5. So I'd like to specifically do page part E. Sounds like a lot of us do have those worksheets on us. That's great. All right, here we have the table. And guess what I'm going to do? I'm just going to take a screenshot of the instructions. That way we can quickly refer to them. Okay. All right. So of course, this topic is daunting. It's a lot to kind of keep track of. It's a lot to kind of remember. There's a lot of areas where you can make very simple, small mistakes that do add up. So I wanted to take a few moments to just really kind of go over this question as a whole to get you to understand that, yes, it might be challenging, but there are ways that you can use to kind of speed things along very confidently. The question asks, for the reaction below, answer the following in the provided table. Number 1 specifically says, distinguish which is oxidized and which is reduced. Part 2 says, identify the reducing and oxidizing agents. And part 3 says, provide corresponding balanced half oxidation and reduction half reactions. Now, let's take a few moments to answer which reactant is oxidized and which is reduced. Going in a little bit further into the reaction equation, we see here, number one, there is an iron. The iron is by itself. The instructions do say assume all elements are in their reference state. So you can freely assume that this iron has a charge of 0. You can also freely assume that the oxygen has a charge of 0. But now they're in the product. So now we have to be sure what the charges of each. We know that oxygen is -2. It's in group 16. How could we have also gotten that? Just reverse crisscross. We could have swung that 2 up. With that same logic, we're going to swing the 3 up to the iron, leading to +3. We can see in the case of iron, if we draw that scale from negative, positive to 0, going to the right is oxidation, going to the left is reduction. We can see here that the iron starts at 0 and ends up 3+. It becomes more positive. This is what tells us that iron is oxidized. Let's go over it once again. Let's take a few seconds just to be absolutely certain. If I formally draw out that scale, so not using that red highlighter, but something that's permanent, we know that to the right is oxidation and to the left is reduction. We have here a situation where we're going from 0 to +3, a very clear oxidation. So we've confirmed it. We're confident. We've taken a few seconds and we've double-checked our answer. Since we know that iron was oxidized, we're confident, the other one must be reduced. I don't need to waste any time confirming it because, as I just did, I spend time on the iron. I'm confident. And we just introduced the concept of agents of redox, where, as it said earlier, what's been oxidized is the reducing agent. What's been reduced is the oxidizing agent. So iron is oxidized. That means it is the reducing agent. Similarly, oxygen is reduced. It must be the oxidizing agent. That took us approximately 75 seconds to get all 4 answers. Very confident in all of them because we spent time confirming one of them, and everything else, like dominoes, falls right into place. So the first 2 questions, which is oxidized, which is reduced, identify the agents, are not meant to be particularly challenging or tedious questions. Have patience when identifying your answer, and everything else falls into place. Now all that's left is to provide the corresponding balanced oxidation reduction half reactions. It says here state symbols are not necessary. So if we get the rubric back, the things that I'm looking for, I'm looking for number of electrons, where they're located, presence of charges, and to ensure that the thing is overall balanced. Focusing on one at a time, I start with iron. I see that iron starts neutral. I see that iron ends up 3+. I have already identified this as being oxidized, so I know that my electrons are going to be on the right. Similarly, I know that since the charge goes from 0 to 3, there are 3 electrons. As of right now, this half reaction shows me the number of electrons, it shows me where they are, it shows me the charge, and as of right now, this half reaction is balanced. There is 1 iron, 1 iron. We can apply that same logic to O2. We see that oxygen starts O2, and we see that it ends up O2 minus. Since this is a reduction, we know that there will be electrons on the reactant side. We also notice the charge. Oxygen starts neutral, it ends up 2 minus. That's what tells us that we'll have 2 electrons. Individually, this half reaction shows me the number of electrons. It shows me where the electrons are. And it also shows me the charges. If you want to be even more particular, you can put a 0 beside the oxygen to be absolutely clear. However, this reaction as written is not balanced. I'm not talking about balance to the other. I just mean within its own room, it's not balanced. How can we see that? Well, there are 2 oxygens over here on the left, and there's only 1 oxygen over here on the right. That's not a problem, though. To balance it, we'll just put a 2 on the right. But something else needs to be updated. Remember, we identify that oxygen starts 0 and it ends up 2 minus. That's what told us that an oxygen will gain 2 electrons. But we don't just have 1 oxygen, do we? We have 2. So you also have to remember to multiply the electrons by 2 to get 4. Each oxygen takes 2 electrons. There are 2 oxygens in total, hence 4 electrons. This reaction as written shows the number of electrons, shows me where they are, shows me the charges, and as of right now is individually balanced. By all intents and purposes, we're done. However, it's on you to purposefully check every time. I see that my individual half reactions are balanced, but are they balanced with each other? No, they are not. This iron is giving up 3 electrons, and the oxygen is gaining 4. That's a mismatch. There's an extra electron that's unaccounted for. So what we're going to do now is we're going to multiply both reactions to get an equal number of electrons. That lowest common multiple. To do that, we will simply multiply 3 times 4. That's what tells us we're aiming for 12 electrons on each side. To get 12 electrons here, we multiply everything by 4. To get 12 electrons on the right, we multiply everything by 3. Resulting in a newly balanced equation. As we can hopefully see, both reactions show the number of electrons. Both reactions show where. Both reactions show charges. And both reactions show balancing not only within themselves, but to each other. This is what tells us that our answer, as of right now, is fully correct. If you absolutely wanted to confirm your answers, look at the balancing of the original equation. If I just erase it so we clear it up. In the original equation, balance had led us to 4 irons on the left, 4 irons on the right, which is exactly what we see here. Similarly, we know there are 6 oxygens in total, and that's exactly what we see in the half reaction. So a couple of students on Wednesday's workshop asked, what do we do with these big numbers? Do we incorporate them? You shouldn't need to try to incorporate them. By the time you're done, you should see those exact numbers. So these numbers in front, the balancing within the context of redox, is there to verify your answers. Meaning, if the balanced equation has a 4, and you wrote a 3 right here, immediately I know you're incorrect. Do we have any questions with this complete problem? Yes, Catherine.
Third part. We put on our diatomic elements.
Yes, because oxygen is a known diatomic. That's how it exists. So it has to be written as O2 in the beginning. Same thing with N2, F2, H2, and the like. The reason why we don't carry that over here is because there's no such thing as just simply O3. So O3 is not the way it normally exists. You just write O. Any other questions? Okay. Now, that sums up the overview of all of the reactions we've covered and their basic principles. Over the last couple of days, we've spent time learning how to predict products, coming down to identifying the archetypes of which there is synthesis, decomposition, combustion, double displacement, and single displacement. And we also saw further subcategories of reactions: gas evolution, a gas is made; neutralization, water and an ionic salt; as well as precipitation, a precipitate is formed; and redox. The handout that I gave you all last week, let me find it. You can see on the very front that solubility rules table. I mentioned already this will be given to you as part of the exam booklet, so you don't need to memorize it. You do need to know to read it. And then the other page is just a summary of all of the reactions we've done and have seen in this class, a few examples, as well as a general description. So this page is not something for you to purposefully memorize for an exam. It's just a summary of the content we've covered so far and should help guide you when you study, since it has a nice categorization of our notes. Our next topic: ionic equations. Ionic equations are just a different way of writing a chemical reaction. Oh, I spelled writing wrong. The basic idea behind ionic equations, or rather the different way we write them, is that we only focus on the important changes. How do we know what an important change is? Well, that's just a change in state. In other words, whenever you see a state symbol change, that's important. The easiest way to teach you about ionic equations is to actually do an example. Since we've been working with that aluminum one already, let's pick that exact reaction back. And we'll go through the steps on how to do this. Take a few moments just to rewrite the equation. I'm just going to erase some of the lines in purple so it's a little bit clearer. Okay. All right. I will have a written way of writing out the procedure, but let's actually do one so you understand what it looks like in full. Then we can actually note some stuff down. First thing, obviously, is that we already have a fully balanced equation. This is one we've already spent time on in a previous class, so we don't need to go back over it from scratch. What we're then going to do is we're going to break apart aqueous species only. And when I say break apart, I quite literally mean break them up. From left to right, aluminum stays the same. Why? Because it's a solid. We need not break it apart. And then we have copper chloride. That is aqueous, so we have to break up the species. This becomes 3 copper 2 plus, 6 Cl minus. I have split up the copper chloride into its respective ions, copper and chloride, and I have considered the relative balancing. There are 3 copper ions. There are in total 6 chlorine ions. When we say break apart, what we're trying to show here is the full ions for all aqueous species. Now, you may be wondering, why did I write 6 Cl? Why didn't I just write 3 Cl2 minus? Well, Cl2 is the element. Let me write it over here. Cl2 is the element. It's a diatomic element, so it can be written like a charge. That's a different thing entirely. So we more specifically write it as 2 Cl minus, of which there are 3, for a total of 6 chlorine ions. Keeping it going, we then have aluminum chloride, which we should again recognize as being aqueous. So we will break this up, and we will include the balancing. We have 2 aluminum, which is 3 plus. And then we have 6 Cl minus, which is aqueous. Again, we've broken up the compound into its respective ions. We've detailed the exact charges, and we have considered the balancing. Finally, we have the copper, which is already solid, so it cannot be broken up. So recognize in this question, we've only broken up half of the species. Sometimes you need to break them all up. Sometimes you need to break some of them up. Sometimes none of the above. After we break apart the aqueous species, we will then eliminate spectator ions. This is a new word, spectator ions. What is a spectator ion? A spectator ion is one that does not change state across the reaction. I like to think of spectator ions quite literally as they sound like spectators. For example, in an athletic game, you have the audience, the ones spectating. Their presence, of course, helps the players play their game. Cheering them on allows them to be better players. But it's not like the spectators, they themselves are actually playing. They're simply there to help the reaction move along, just like the audience members at an athletic game are just there to help the players play better. So to identify spectator ions, we simply go chemical by chemical and identify, has it changed or not? Starting with aluminum, we see that it starts solid and it ends up aqueous. This is a change. This is not a spectator. Copper starts off aqueous. We see that it ends up solid. This is a change. It is left alone. Finally, we have chlorine, which starts off aqueous and ends up aqueous. This does not change state. This is a spectator ion and is concomitantly eliminated. We write what's left, which is 2 aluminum solid, added to 3 copper 2+ aqueous, gives us 2 Al 3+ plus 3 copper solid. This right here is known as our net ionic equation. And that one that we drew in the middle, the one that had all of the ions, that one's known as the complete ionic equation. You can rest assured that I will almost specifically only ever ask you to write the net ionic equation. But throughout your process, you will make the complete ionic equation. Now let's talk a little bit about that kind of importance factor. Why exactly this is so useful, why it's just a different form of writing an equation we already know. You see, the utility of an equation like this is that it tells us, the reader, the audience, the person who wants to invest in this chemical company, that, hey, when I react aluminum and copper, if I were to just get some pure aluminum and I were to react it with copper, then what I would end up with is pure copper solid. The reason why some things like this become so useful is because some elements, such as copper, can be really expensive. Maybe it costs $1,000 per pound. Why? It's a transition metal. Transition metals are rare. They need to be mined. It's a little bit more expensive, blah, blah, blah. But copper 2+, aka in a compound, that can cost like $250. It's a lot cheaper. It's not pure, it's a compound. Similarly, something like aluminum, used very commonly in construction, that might cost around $500 per pound. So what I'm trying to tell you here is that a person who's reading this equation says, oh my God, instead of spending $1,000 buying copper outright, I can spend a cumulative total of $750, get one of my lab assistants to run the reaction, and all of a sudden I've made my copper, saving my group $250. Now, this is just one reaction. Think about on a larger scale in a company. Pharmaceutical companies, petrochemical companies, these types of ideas will help them save millions, even up to billions of dollars a year. So its utility isn't that, hey, this is a really cool chemical reaction that has never been done before. No. The utility of ionic equations is that it helps us understand important reactions and helps us determine cost-cutting measures. Instead of buying $1,000 of solid pure copper, I can spend a collective sum of $750. Takes like 10 minutes to run the reaction. All of a sudden, I've saved $250. Do we have any questions on ionic equations? Yes, Prab. Very good question. This is actually a completely different topic from redox. So electrons don't matter here. We just simply took this equation because it's the one we most recently worked on. Let's try another one from your worksheet, from last week's workshop. Where is it? Now, if you recall, part of last week's workshop, there was a question. I'll show you right here. problem 3b. Problem 3b says on a separate page, meaning I'm not printing paper for you. You can either write this on white paper or lined paper. But on a separate page, provide balanced net ionic equations for all reactions from problem 3a. State symbols are not necessary. If no net ionic equation exists, state so. So this is the kind of question you can expect on your upcoming exam. So let's take a second to try one of these questions and complete it. Because Prob points out, well, what about the electrons in this case? Why doesn't that matter? Well, we're not really talking about electrons. I'm just giving you a reaction and telling you what to do. So I'm going to do it for LL. And then once we're done with LL, you will then do MM, or the next one, on your own. You can see on the whiteboard in front of us the full steps to generate an ionic equation. Number one is to write the fully balanced equation first. We can see as of right now, we don't have that at all. So we need to take a second and identify it. We have calcium hydroxide, solid, reacting with sodium nitrate, aqueous. And now we need to fill this out. We have to predict products first, which means we have to identify the archetype. We recognize this as a double displacement, A, B, C, D. That gives us A, D plus C, B. How do we predict products? The first thing we're going to do is match ions. A ends up with D. C ends up with B. NaOH. Now I'm going to check charges and crisscross as needed. Sodium is in group 1, so +1. Hydroxide is a polyatomic ion. It is -1. This is a case where the charges line up, no crisscross needed. NaOH is correct as is. We have calcium, which is in group 2, hence it's 2+, and nitrate, a polyatomic of -1. Charges do not line up. Crisscross is necessary. The 1 goes down, the 2 goes down, leading to calcium nitrate and sodium hydroxide. As of this moment, all I have done is matched ions and crisscrossed. Now I'm going to put state symbols. As a nitrate, all nitrates are aqueous, no exceptions. Hydroxides are also aqueous. Sodium is not an exception. So sodium hydroxide is aqueous. Now we're going to balance the equation from left to right. 1 calcium, 1 calcium. 2 OHs, 1 OH. No big deal. Just put a 2 in front of it. Calcium is balanced. OH is balanced. 1 sodium, 2 sodium. No big deal, though. We're just going to put a 2 in front of it. Calcium is balanced. OH is balanced. Sodium is balanced. 2 nitrates. And oh my God, would you look at that? 2 nitrates. Yet again, another situation by balancing in order. By the time you're done, everything will be balanced. This reaction, as written, is correctly balanced, correct state symbols, and correct products. So now we know the full answer to up here. Recognize that we haven't even started talking about ionic equations yet. All I have done is provide a complete balanced equation for the reaction. This will be worth 3 points. 1 point for products, 1 point for balancing, 1 point for state symbols. Now that we have a fully balanced equation, we're going to generate the ionic equations. Following the steps on the board, the first thing that we do is we're going to write out and break up all aqueous species. So the first thing we're going to write is the complete ionic equation. From left to right, we have calcium hydroxide, which we do not split. Why? It's a solid. Then we have sodium nitrate that we do split because it's aqueous. Then we have calcium nitrate, which is in fact aqueous. And then we have sodium hydroxide, which is, of course, aqueous. So pretty much 3 out of the 4 compounds here get broken apart. After breaking apart aqueous species, we're going to eliminate the spectators. The spectators are those that do not change state across the reaction. Calcium starts off solid. It ends up aqueous. This is a change. We leave it alone. OH starts solid and ends up aqueous. This is a change. We leave it alone. Sodium starts aqueous and remains aqueous. This is a spectator, hence deleted. Nitrate starts aqueous and remains aqueous. This is also a spectator and is concomitantly deleted. Once we have eliminated all the spectators, we will then write the net ionic equation. We have calcium hydroxide, solid, which results in calcium 2+, aqueous, added to 2OH, aqueous. The net ionic equation is approximately worth 2 points. So put another way, if this were a question on the exam, if I were to give you the reactants and simply say, provide me the net ionic equation, it would be worth a sum of 5 points. Does anyone have any questions on the reaction between calcium hydroxide and sodium nitrate? No? Okay. Take about 5 to 7 minutes to do the next one. I believe that's MN or MM. That's a reaction between zinc and copper sulfide. Work it from the very scratch as if though this were an exam question and assume that it'll be worth 5 points total. I'll walk around and help out wherever I can, and in 5 minutes, we'll go through it together. Just so there's no dead air, I'm going to pause the recording on Zoom. Resume recording. The recording is live. I have enough space here? No, I don't think I have enough space here. Let me write it on the other page. All right. So the next question is as follows. Zinc added to copper sulfate. And of course, the overall question that we're being asked here today is provide the net ionic equation. From the steps on the board, we see that very first step is to write the fully balanced equation first and then work from there. So the first thing we have to do is predict products, balance, match ions, all that nice stuff. This is where those reaction archetypes come handy. We should recognize this as an example of single displacement. A plus B, C gives us something else, where A will either replace B or it will replace C. Looking at the possible options, copper is a transition metal. Zinc is a transition metal, meaning, if anything, A will replace B. That's what tells us our final answer should be something like AC plus B. Matching ions together, we get zinc sulfate and just copper. Now we're going to check charges over here on the right. Copper ends up by itself, so no charge. Then we have zinc and sulfate. Sulfate, a polyatomic ion, is 2-, and here we have zinc. Zinc is a transition metal, so we cannot just look at the periodic table and figure out what its charge should be. As we've talked about, I need to give you some information or hint to figure it out. Over here, since we recognize the zinc will replace the copper, and logistically, it should also take its charge. The sulfate is 2-. The fact that there is a 1-to-1 ratio of these guys tells me that copper is 2+. So when that neutral zinc replaces copper, it also becomes 2+. And since we know sulfate is 2-, this leads to 1-to-1. The formula is balanced as is. From there, we will then incorporate state symbols. Zinc sulfate is aqueous by all rules. Copper by itself is a transition metal, so it's solid. Now we're going to overall balance the equation. 1 zinc, 1 zinc. 1 copper, 1 copper. 1 sulfate, 2 sulfates. The equation is balanced as written. That is now step 1 out of the way. The fully balanced equation is done. Now we're going to break apart our aqueous species. Zinc remains zinc. Copper sulfate becomes copper 2+. SO4 becomes SO4 2-. Zinc sulfate becomes zinc 2+. And sulfate 2-. And then nothing happens to the copper as it's a solid and left alone. Now that we've broken apart our aqueous species, we're going to eliminate the spectators. Zinc starts off solid. It ends up aqueous. This is a change. It is left alone. Copper starts aqueous. It ends up solid. This is a change. We leave it alone. Sulfate starts aqueous, ends up aqueous, no change, hence eliminated. The final answer, of course, is the net ionic equation that shows zinc and copper 2+ reacting together to form zinc 2+ and copper solid. And this right here is our final answer. Hopefully, as we are working through the question / recognizing our mistakes, we're starting to see the cumulative nature of this class. There are a lot of things going on here to ensure that we got this correct, that we did it successfully. You needed to remember ideal charges based on groups. You needed to remember polyatomic ions and their charges. You needed to remember reaction archetypes, state symbols. There's a lot going on here So when you practice, I recommend getting a pen and paper or pencil and writing everything out. If you're a type of student that prefers to use the whiteboard, by all means, use it. Write, erase, write, erase. Muscle memory is your biggest friend in these kinds of questions. As you practice more and more, don't be surprised if your body starts telling you something is wrong before your mind tells you it's wrong. Let's do another question just for completeness in the time that we have left. I would like to do II. So you can see it already up here on the screen, II. All right. The question is, as per all the others, provide the net ionic equation. So the very first thing we need to do is predict products. Recognizing that this is a double displacement, we get AB plus CD to give us AD plus CB. Matching ions tells us this will be NaCl plus HCO3. All I've done is match the ions together. Now I'm going to check charges. Sodium in group 1 is +1. Chlorine in group 17 is -1. So it's balanced. It's fine. Hydrogen in group 1 is +1. Carbonate, a polyatomic ion, is 2-. We do need to crisscross here. That 2 goes down to become H2CO3. Now we're going to balance the equation overall. We have 2 sodiums on the left, 1 on the right. That's an easy fix. Just put a 2 in front. Sodium is now balanced. We have 1 carbonate on the left, 1 carbonate on the right. 1 hydrogen on the left, 2 hydrogens on the right. Easy fix. Just put a 2 in front of the HCl. Sodium is balanced. Carbonate is balanced. Hydrogen is balanced. We now have 2 chlorines. And to no one's surprise, we already have 2 chlorines on the right. All that's left is state symbols. Sodium chloride is aqueous. H2CO3 is also aqueous. Is this correct? Listen to the tone of my voice. All I've done so far is pull the fully balanced equation. That's all I'm asking you. Is this fully balanced equation, as written, is it correct? Use the tone of my voice as a hint. Is it correct or not? I see a couple of yeses. Does anyone want to say that it is not correct? It is not correct. Why? Because H2CO3 was that weird, curious case that we talked about when we did gas evolution. Whenever H2CO3 is formed, it will always break up into H2O and CO2. You are responsible for remembering that and applying it. So the correct answer here, if I were to write actually, we have sodium carbonate plus 2HCl to give us 2 NaCl plus H2O plus CO2. And this comes back from you remembering that H2CO3 will always break up into H2O and CO2. This is what I mean by muscle memory can be your best friend. Because even if you may not remember off the top of your head, H2CO3 does this. If you do enough questions, your body will be telling you, wait, something's wrong. Check this. We're not done yet. All we've done so far is write the fully balanced equation. Next up, we're going to break apart aqueous species. This becomes 2Na plus, CO3 2 minus aqueous, added to 2H plus, 2Cl minus, resulting in sodium chloride, which does get split up. Added to H2O liquid and CO2 gas. Notice that I did not split the H2O or the CO2. The reason should be obvious. Neither one of them are aqueous. So they get left alone. From left to right, sodium starts aqueous, ends up aqueous. This is eliminated. Carbonate starts aqueous, and we recognize that it ends up some sort of cacophony of the H2O and CO2. It doesn't matter the details. What matters is it's changed, so we leave it alone. H plus starts off aqueous and ends up part of liquid water. This is a change. We leave it alone. Chlorine starts aqueous. We see that it ends up aqueous. This is eliminated. The resulting answer, the net ionic equation, is therefore CO3 2 minus aqueous added to 2H plus aqueous gives us H2O liquid plus CO2 gas. And this right here is our final answer. A lot of stuff to keep track of. I see your hand. A lot of stuff to keep track of. When studying, it's not enough to just read. I do recommend doing practice problems. As you know already from my first exams, my questions are mostly application-based. Very rarely do I have like rote memorization questions. I saw a hand over here. What was it? What was your question? Correct, because neither of them are aqueous. We only worry about charges and breaking up if they're aqueous. If they're not aqueous, we just leave them as is. Any other questions? All right, in the time we have left, we don't have enough time to do another question, so we'll end lecture for today. We do have a wet lab today at 1:30. I'll see you all in 6:04 in about 19 minutes. If there are any questions, you can come talk to me now. Otherwise, I'll see you then.